The last part of chapter 9, I think, is not too bad. It's all double angle identities. These are identities that are actually in the formula booklet, so you won't need to memorize them. There's all these long investigations that I don't know that it really does much for you to actually do it. So I'm just going to skip right to the actual identities. All right, so double angle just means I'm multiplying the angle by 2. So that should make sense. Sine actually has only one that it equals. And cosine, there are 3 different identities that you can use. All 3 of them are in your formula booklet. There are times when the top one is the easy one. There are times when you'll use one of the bottom ones to get everything into one variable. But we use all of them in different situations. Okay, so what people struggle with when they see this, they don't understand you can't just plug stuff in. Notice this says sine of alpha, cosine of alpha. So we need to replace sine of 2 alpha with what it equals. So because sine 2 alpha equals 2 sine alpha cosine alpha, this formula is just this side. So now what you can do, sine alpha equals 3/5, cosine alpha equals -4/5. So I'm going to substitute 3/5 in for sine of alpha. Sometimes it helps to put that 2 over a 1. Cosine alpha is -4/5. Now we just multiply the top, multiply the bottom, and we're done. So that's an example of your sine double angle. All right. If you know both sine and cosine, I think the easiest one to use is the top one. You can get the answer with any of them, but I'm going to use the top one. So I'm going to replace cosine. Oh, and I should always match my variables, right? So cosine is -4/5 squared minus sine is 3/5 squared. Now we just square them. 16 25ths minus 9 25ths. Subtract, because this is why I like this one, is you have common denominators right away. Done. Okay, with letter C, we can just cheat. There's actually a double angle for tangent. It's a little annoying. But what do we know about tangent? It's just sine over cosine. And didn't we find sine 2 alpha in the first problem, letter A? We found cosine of 2 alpha in letter B. We have our fraction over our fraction, so we multiply by the reciprocal. The 25 cancels, and we get -24/7. So that's your general way that you can use the double angles. Okay, this one we only know the value of sine, but they also tell us where the angle is at. It's more than pi over 2, but less than pi, which means it's in the second quadrant. So if sine is 5/13, y over r, we would use our Pythagorean theorem. But if you remember, we have a 5, 12, 13 triangle. If you did not remember that, you can just do 5 squared plus b squared equals 13 squared. and solve it out. And because I'm in the second quadrant, that means x is negative. All right. So sine 2 alpha, I need to replace this with what the formula is. So whenever you see that 2 alpha, look in your formula booklet. It gives you the formula. 2 sine cosine. All right, so I'm going to keep my 2 over 1. It's always 2 over 1. Sine, we knew right away, was 5 over 13. They told us that angle was in the second quadrant, so I could find what cosine was equal to. Negative 12 over 13. Multiply the top, multiply the bottom, and we're done. Okay. This one's a little bit trickier. When it shows us the cosine double angle, remember how I said there's 3 of them? If we just want to find, oh shoot. All right, false fire alarm. Sorry about that. All right, so I'm going to write out my cosine double angle that just uses cosine. All right, I can't have a 2 here, but I can have it squared because I can get rid of the square by taking the square root. All right, so it says in the problem that cosine 2 theta equals 3/4. So we can just substitute 3/4 in place of it. Now I'm just going to get cosine by itself. Add 1 to both sides. 3/4 plus 1. That's just 1 3/4 or 7/4. Divide by 2. And when you divide by 2, you're just putting the 2 in the denominator. So now I have 8 in the denominator. Square root both sides. And it tells us in the beginning that our angle is acute, which means that our cosine is the positive square root of 7 over 8. If it didn't tell us it was acute, we wouldn't know if it's a positive value or a negative value. Okay. Now, if I know what cosine is, I can use the cosine value to find the sine because I know that sine squared plus cosine squared equals 1. Do you notice how often we've used this identity? This is our Pythagorean identity that connects sine and cosine together. So I can replace cosine with the square root of 7 over 8 squared. This one's okay because when I square my square root, it's just 7/8. Then I'm going to subtract 7/8 from both sides and get 1/8. Square root both sides. Once again, the angle is acute, so I want the positive. And technically, the square root of 1 is 1, so I could simplify that. So these are my 2 answers. So we're going to use this identity a lot. All right, last one. So which is the one identity that uses sine times cosine is 2 sine cosine, Well, what could I multiply this by to get 3 sine cosine? I could, if I multiply this by 3 over 2, wouldn't you agree this is really just 3 sine cosine? So I'm going to manipulate this with an identity that we know, because I can now replace 2 sine cosine with the double angle 2 sine of 2 theta. So if I multiply this times this, it actually will simplify back. And last but not least, notice there's a GCF of 2. We have 2 cosine squared minus 1, which is cosine of 2, whatever this is. Normally we say 2 theta, but right now that's 2 beta. All right, so I have 2 of the 2 betas. But what's 2 times 2 beta is 4 beta. And that is section D.